Para esta tarde queremos presentarles a Rafael Silva con este tema que es Generador de Espectros Planetarios, Modelización y Comprensión de los Espectros de las Atmósferas Planetarias para el estudio de las ciencias planetarias. Él es interesado en el estudio de las atmósferas planetarias dentro y fuera de nuestro sistema solar. Se licenció en Física en la Universidad de Lisboa en 2021 y se graduó en el Máster en Astrofísica de la misma universidad en febrero de 2023. Su investigación sobre atmósferas planetarias en el Instituto Portugués de Astrofísica y Ciencias del Espacio se ha centrado en la recuperación química de compuestos atmosféricos menores utilizando espectros de alta resolución de algunos de los mayores telescopios ópticos del mundo, como el Very Large Telescope, VLT, de ESO en Chile. Durante su tesis de maestría, ha desarrollado un nuevo método para analizar espectros de alta resolución del VLT que ha permitido la detección de nuevas líneas de absorción visibles de metano, así como una detección tentativa de una especie química C3 en la atmósfera superior de Titán. Su objetivo es contribuir a las ciencias espaciales y planetarias mediante el estudio de las atmósferas planetarias, cuya composición química y estructura son observaciones clave que reflejan la evolución temporal de los planetas, con algunos marcadores químicos que posiblemente indiquen la existencia de procesos geoquímicos en el planeta o incluso de vida. Entonces, Rafael, bienvenido a nuestra charla, a la tercera charla de la Red Boliviana de Ciencias Planetarias y Exploración Espacial. Te agradecemos muchísimo por el tiempo para compartir las investigaciones que realizas y sobre todo por la disponibilidad de hacerlo también en español, que no es tu lengua nativa, para que podamos hacer de esto de manera más dinámica y que sea más fácil también. Por favor, gente, si alguien tiene alguna consulta en medio de la presentación, puede presionar la manito que está en la parte inferior de la plataforma para que yo le vaya diciendo a Rafael cuando haya alguna consulta y así vamos resolviendo las dudas a lo largo de la presentación. También pueden escribir el mensaje en la parte de mensajitos o pueden alzar la mano para que yo les dé el espacio para que ustedes puedan hacer la pregunta. Ok, entonces, Rafael, te doy espacio libre para que tú puedas empezar a compartir tu pantalla y hacernos la presentación.
Gracias. So I'll switch to English now. Again, I would love to give the talk in Spanish, but my knowledge of Spanish works for chatting a little bit like this, not for scientific terms. So if anyone doesn't understand English or doesn't understand anything that I've said, please be free to ask the questions that you may have in Spanish, and I'll understand them and I'll be able to ask them back, to answer them back. Okay. So I'll start sharing my screen. As I said, this will be a little bit slow because my computer is running some simulations, so it's all a little bit slow. But I think I can share it now, and you may be able to see it like this. It's taking some time.
Now I see your screen, but not in the presentation mode.
Not in the presentation mode. I've just clicked the presentation mode. Let me check. Can you see it in the presentation mode now?
No yet. I think it's just taking its time, just a little bit.
Some time. Yes, I can see it in presentation mode now. You see it already?
No yet.
Rafa, I think that you need to share your whole screen.
My whole screen, yes, of course.
Yes,
so I'll try that. Okay.
Mientras tanto, quisiera recordar a la gente que también si encuentran alguna palabra en inglés que no reconocen, también la pueden ir colocando en los mensajes para que podamos ir complementando esa información.
So maybe can you see my screen now?
Now I see it. Thank you.
Okay, thank you. Thank you so much. So, so thank you so much once again for having me today. And what I'll be telling you about today is about this very useful tool that I've used a lot of times since my bachelor's degree through my master's, and I'll keep on using for sure, which is the planetary spectrum generator. Why is this important, and why have I decided to talk about this in this workshop after being invited here by Nicole? This is a tool that is publicly available for everyone online, so you can all use it, and it's very useful as a way to model the atmospheric spectra of planets and exoplanets without needing too much knowledge of computer codes and very complicated computer codes. You can do it online, and it's very useful as a way to understand how planetary atmospheric spectra work and which information can we retrieve from observations through this modeling. So we use these models and simulated spectra of planetary atmospheres to compare with the observations that we conduct. And that's basically why we need this modeling part close together and being developed at the same time as we develop observations of other planets and exoplanets. So I'll tell you a little bit about this method, which is a simple one that allows us to simulate planetary spectra. And I'll tell you about it. This is sort of the motivation behind this. So as I told you, I'm working towards becoming a planetary astrophysicist. So I'm really interested in planetary sciences, and I'm really interested in which stories the evolution of the different planets within and beyond our solar system can tell us about even our own planets or the diversity of planets across the universe. So if you look in our solar system, we have two main kinds of planets: the giant ones, the gas giants, and of course there are the rocky planets, which have very different kinds of atmospheres. So if you look at planets like Jupiter or Neptune or Uranus or Saturn, so their atmospheres are really large, bloated. They're dominated by hydrogen and helium gases, and have as minor compounds methane, which is CH4, water, H2O, ammonia, phosphine, and diverse hydrocarbons or nitriles or other more complex species that result from the photochemical dissociation of these simpler gases in their atmospheres. And their distinct colors, so these different gases color distinctly the different bands and clouds within these planets' atmospheres. And as you observe them in different wavelengths of light or in different colors, we obtain the spectra of these planets. And it is the spectra of these planets, so how the light of these planets is split within several wavelengths or colors, as we may call them, tells us about the distinct compositions that these planets may have. At the same time, while we look at rocky planet atmospheres, we see that they're not dominated by, they don't have hydrogen, they don't have helium, they have very little methane, if any at all, and they're actually dominated by either CO2 or nitrogen gas. So Venus and Mars are dominated by carbon dioxide. On Earth, we have a mechanism that basically keeps carbon dioxide from building up in the atmosphere, which is the fact that we have oceans. So because of that, CO2 does not matter immensely for the composition of the planetary atmosphere of Earth, but of course it's very important as a regulator of the Earth's climate. So most of the atmosphere of the Earth is dominated by nitrogen gas. Of course, we have oxygen, and we have some other smaller compounds, all of them much more oxidized than the previous compounds that we see in gas giants, so like water, carbon monoxide, carbon dioxide, sulfur dioxide, and several others. And I've put here as a comparison James Webb's spectrum of Mars atmosphere, in which you can see detections of carbon dioxide, of carbon monoxide, of water, and on contrast, the spectra of Jupiter and all of the other gas giants, as well as Titan, in which we have detections of methane and several other of these more reduced compounds. And this is just the motivation for my talk. So how can we study the chemistry and the vertical structure of other planets' atmospheres, and what can we learn from them? So what does the fact that the Earth has different atmospheric compositions than Mars or Venus tells us about the evolution of Earth itself, or the evolution of these other planets? So that's really the reason why we're so interested in probing the atmospheres of other planets, to understand, because they're much more observable. They're just really what separates the planet and the outer space, and they're really easy to observe if we have the right mechanisms or tools, which is what I'm going to tell you about today. So to do this work, and this is just a very short introduction, we see the planets through the radiation that they end up leaving that leaves the planet towards the space. So there's two types of radiation mattering to the planet's radiative transfer and radiative balance. So the planets do not have their own proper light, so to say. So all the radiation that comes into the planet, most of it, or a vast majority of it, comes from the solar or the stellar radiation falling into the planet. And this radiation, of course, is either absorbed by the atmosphere, or reflected by the surface, or absorbed by the surface, or scattered by aerosols or hazes that the planet might have. And some of it is reflected right back to space. So if you look at a planet, at the same time, the surface warms up a little bit and it starts emitting in thermal radiation. This is not in the visible part of the spectrum, it's in the infrared part of the spectrum. And this part of the radiation is the one that is absorbed by greenhouse gases. So some of it can come down and keep the planet warm, as is the case on Earth, and is an exaggerated case on Venus, for instance. But at the same time, some of this outgoing radiation, long-wave radiation, which is in the infrared, comes out of the planet and carries with it the information of some of the molecules that are present in the planet's atmosphere, either because the radiation lacks specific specific wavelengths or colors that are being absorbed by given gases in the atmosphere. And through looking at these outgoing and reflected radiation coming out of the planet, we can see what the planet's atmosphere is made of. And we can study, for instance, its vertical structure. What is the vertical structure of a planet's atmosphere? Well, basically, it's how the pressure and temperature, or vice versa, or the temperature evolves with pressure as we go higher and higher in the planet's atmosphere. And I don't want to get into much detail here, but the fact that you have clouds and photochemical process in the planet's atmosphere really shapes these curves, these specific graphs that are true for each planet's atmosphere. So by studying these and by retrieving these vertical profiles for each atmosphere, we can understand a lot of processes that are happening on the planet's atmosphere, understand a lot of stuff about the planet itself. So this is one of the goals as well that we have when we retrieve spectra from planets, to also to understand not only their composition, but how the temperature and pressure vary as we go down and down in the atmosphere. So again, just as a quick reminder of what this whole thing about spectroscopy is that I'm talking about, well, white light can be divided into its several colors, which form what we call a rainbow. But of course, as we split a planet's light that is coming through these processes that I've just described about, well, we don't see a complete rainbow. We see some colors missing. These are what we physicists like to call wavelengths, and they are not there because of the absorption of given molecules in the atmosphere. So each molecule absorbs at each specific wavelengths That's why we can call it a little bit like a fingerprint of the planetary absorption. And if we see some of these energies or wavelengths lacking in a planetary atmosphere, well, we can point and look at their wavelength, see their intensity, and say, well, this is water absorbing something in the planet. So it means that there's water or hydrogen or any kind of molecule that has those specific signatures within a planetary spectrum. So this is what we're really looking for as we try to detect new molecules on a planetary atmosphere. And of course, we do this also for exoplanets. Sometimes we have the planet transiting over the star, right in front of the star, and if you subtract the light of the star with the planet in front of it from the light of the star, just without the planet being in front of it, you can see some of the, if you subtract one spectrum from the other, you can see these lines that are lacking due to the presence of the planet and due to the presence of the planet's atmosphere. And from that, detect chemistry and winds even in exoplanets that are light years, tens of light years away from us, which is pretty incredible. Of course, we need observations, but to interpret these observations, we need to model these spectra. So, for instance, for my master thesis work, I've used data from the VLT telescopes, which are in the Atacama Desert, quite close to you in Chile. And the fact that we have these great instruments that we can apply for time on them is a great thing. That as part of, since Portugal is part of the European Southern Observatory, which builds these telescopes, we invest there, we build these telescopes even here in Lisbon, and some of the instruments here in Lisbon. So then we have some time that we can apply to use and get some time from these telescopes. And they are quite huge. I don't know if any of you has had the experience to go there and watch it. I haven't yet, but I'm really looking forward to go there one day. And they're massive. Some of the telescopes are so these 4 larger telescopes are about 8 meters wide, and so they have an 8-meter diameter mirror that is able to obtain spectra for basically whatever planet or star or galaxy you want to observe. And then the spectra basically comes out like this. There's lots of processing that goes through it, and what you see is basically this line that has a spectral dimension, so the different colors go this way, and you have the planetary disk being stretched in this direction. And in some places you see a little bit less light coming from the planet, which means that there are something absorbing this light coming from the planet, and that's how you obtain those spectra I told you about. So okay. Just as an example of what low resolution spectrum or higher resolution spectrum looks like for our planet, this is a textbook example of planetary atmosphere spectrum, which is that of Titan. You can see that here we have the visible part of the spectrum. This part is the infrared part of the spectrum, and this part is the ultraviolet part of the spectrum. And we see that there are several processes. So the higher the value is here, by the way, is how much the planet is reflecting the sunlight. So the higher the value, the brighter the planet is for that specific color. For instance, Titan is brighter in reddish wavelengths than blue wavelengths. So if you were there to look at it, it would look a little bit more orange or reddish than blue or white. And this happens because there's plenty of effects shaping the planetary spectrum. So the intensity of light coming out of the planet as a function of wavelength. So we have Rayleigh scattering, which is basically small molecules in the atmosphere absorbing more light for smaller wavelengths. This is basically the reason why the Earth's sky is blue, is because of Rayleigh scattering. The same thing happens in Titan. But in Titan, you also have haze absorbing. Haze is basically lots of aerosols, lots of very small particles and in the atmosphere that are made from the photochemistry happening in the planet that you see either absorbing or scattering light. And this also affects the shape of the spectrum. And then you have all these huge dents on the middle of the spectrum. that are caused by methane absorption bands. So there's the majority, so there's not the majority, but a very important gas in the atmosphere of Titan, which is methane, that very strongly reacts with light in the infrared part of the spectrum, and it absorbs a lot of that light. So in the places where it absorbs, you see these bumps in the spectrum because some of the light is being absorbed by the methane in Titan's atmosphere. So if you know where the methane is absorbing, then you can even estimate the amount of methane and how much each molecule absorbs out of the incident light. You can even retrieve the amount of methane in each part of the Titan's atmosphere. So this is something really cool to do. Another thing I wanted to tell you about is spectral resolution. So here we are talking about low resolution. What does this mean? Low spectral resolution. What does this mean? So here we are spreading the light that's coming, and you can see a wide part of the wavelength spectrum. You can see from ultraviolet to red, to the red and infrared part of the spectrum. And because of that, you cannot see in very high detail. You cannot see individual absorption lines. You see absorption bands, which are a lot, many absorption lines together. So that's why you cannot see a single absorption line here. This is like thousands and thousands of absorption lines of methane. Now, in the next plot, I'll show you some of the data I've been working with, which focuses on this small part of the spectrum, but it focuses on, so here I'm zooming into that part. And what you see is that this is a high resolution spectrum. It's about 100 times higher resolution than the previous one. And what you can see is individual lines that are actually coming from the sun, because these are solar absorption lines that are being from the sunlight that is being reflected from Titan and that we can see here on Earth. But in the middle of it, you can see some of these dents again that are the absorption bands of methane. So some of these lines here are actually caused by methane absorption in Titan. And we can, so some of the methods I've used and developed during my master thesis allow us to distinguish between solar and methane absorption bands. So between solar absorption lines and planetary absorption lines. So this really comes to show, I really wanted to make it very clear the difference between a high resolution case, as it is in this case, in which you can see each individual absorption line, and the previous case in which you basically can only see an average for each wavelength, but at the same time, you can see a much wider part of the spectrum rather than just this very tiny part of the visible spectrum that doesn't even cover the whole thing. So high resolution, you can see a lot in detail, but only a short part of the spectrum. Low resolution, you can see a lot of the spectrum, but with not as good resolution. So that's the difference here. So then what I wanted to tell you about today is how do we model these planetary spectrum? So this is done by this, can be done by this tool, the Planetary Spectrum Generator, that combines information about the planets we want to characterize, about the atmospheric composition of the planets we are analyzing here, and also any doubt in your side? Is everything okay? Just wanted to make sure that everything is all right there. Are you still listening to me? Are you still there?
I think there is no questions by now. Everything is listening to you. Everyone is listening for you.
I just wanted to make sure if my connection was still good, because I was not hearing it. It was already 20 minutes. I just wanted to make sure if you're all following and if my connection didn't fall, because I really can't see you. So what I wanted to move on now is to talk about these different factors that are important to consider when we model the spectra of a planet. We have the planetary characteristics, which we can vary in this model, which is the radius of the planet, the mass of the planet, the orbit of a planet, the geometry through which we observe the planet. Is it going to pass in front of the star, or are we going to look at it to the other side of the solar system? Or is it around another star? Or is it a transiting exoplanet or not? Then we have information and we can pick and choose the atmospheric composition. This includes the vertical structure, the different gases and their compositions in the atmosphere, if there are clouds, and what clouds. Water clouds, CO2 clouds, ammonia clouds, hazes, or aerosols in the planet's atmosphere. And then the other thing that matters is the kind of instrument with which we're observing. And this planetary spectrum generator tool basically has all this information, so you can adapt the diameter, the noise of the instrument. If you're using Earth or a Earth-based or a space telescope, so it matters if you're having the Earth's atmosphere in front of your spectra or not. And of course, the spectral resolution I told you about before. Now, this is just an example of this tool, the Planetary Spectrum Generator. You can literally just Google it and you'll be able to open it. And this is what it looks like. You have, again, these three commands here I told you about, in which you can change the characteristics of the object. You can change the composition of its atmosphere, and then you can change the instrument with which you are going to use it and its characteristics, resolution, wavelength, coverage, even the exposure time, so that you can have a higher or lower noise in your data. And then you can just click down here, generate spectra, and you'll get a spectra of that planet's atmosphere. Here's an example of what I got for simulating Titan spectrum in the visible part of the spectrum. And as you can see, we have these bumps again that are caused by methane absorption in Titan. So this is just an example of why having these spectra is important, because then you can compare it with your observations. And then you can get, for instance, you can simulate 10 spectra of your planetary of interest, and you only vary like one abundance, like the abundance of this C3 gas that I tried to detect in Titan. So you can see these are different spectra models that I created. I did not use Planetary Spectrum Generator, but because it was a little bit different, but doesn't matter for the case. You can simulate different spectra with different amounts of the gas that you want to detect, and then compare the differences that more or less of this gas cause in the spectrum, or in the simulated spectrum, and then compare it to the real spectrum. And then you can see here that where you'd expect the differences to be present is where the planet is going to absorb due to the presence of this gas. And again, this allows us to detect some new molecules, as was my case here, and it's published in this article if you're interested to watch. Again, just before I move to the other part that I wanted to share with you, I just wanted to say that we can also model exoplanets. We can model them as they pass in front of the star, and we have several templates in Planetary Spectrum Generator that you can use it, which is really, really interesting. And of course, you can also use information from upcoming observatories or even existing observatories like James Webb, Ariel, Hubble Space Telescope, and compare it with data that is publicly available. So you can, if you're interested in it, you can write a Python code, for instance, that will produce a spectrum that will get you basically the spectrum that is publicly available. You can find it in a TXT file, for instance, of this hot exoplanets, and then you can go to Planetary Spectrum Generator, as I'll show you, and simulate the spectrum as I'll show to you now. And then you can compare it to both of them. You can vary some of these amounts of gases in the atmosphere, and through that you can really conduct your own detections of these gases in the planetary atmospheres. Just before I finish this part, I wanted to say that, of course, all this work that I do is teamwork. It's very important to work in teams. This is my institute here in Portugal. If you're ever coming to Portugal, please say something. We're very happy to show you around our institute and our old observatory, which is a lovely building. And before I wrap this thing up, I wanted to actually show you the Planetary Spectrum Generator tool. Are you seeing it being shared now?
We're watching your some web page that you're trying to open.
I'm trying to open this Google page, which again, my computer is a little bit slow today, but it's already appearing here. So this is the Planetary Spectrum Generator, the tool I told you about. So as you can see, you're all seeing it here. Can you see Mars spinning here?
Yes, we see it.
Okay, that's great. So what you have here is this tool I told you about. So imagine that you want to produce a spectrum of Mars. So they have several templates here. You can choose whatever you are interested in, and you can do, for instance, let's do this Mars as seen from JWST, so James Webb Space Telescope. So I've uploaded the template, and then I'll check what information we've got here. So we can go here, change object, and here you can change Mars to any planet you want. You can put Earth instead. Here it appears, Earth appears here. The planetary characteristics such as distance to the sun, the radial velocity, the length of the day, and the viewing geometry with which you view the planet also changes. I'll put Mars again here. There it is. And of course, the distance to the sun changes, the size of the planet alters, as well as its density and everything. If you're fine with these results that we have, and move on to the next part, which should appear now. It's a little bit slow again. Sorry.
While we're waiting for that, we have one question for you.
Yes, please.
I'm gonna read it in Spanish, okay? Dado la cantidad de datos que se maneja para el análisis de espectro, ¿utilizaron algún sistema informático o inteligencia artificial que ayude en el análisis?
Actually, it's mostly us doing the analysis. So we have a lot of we do a lot of coding in astrophysics, and this program actually does all the very complicated equations that it does all those equations by itself, so that the only thing you as a scientist have to do is to compare the spectrum with the observations that you're doing, and then do the science, then decide if the model fits or not. Then again, you can do this with artificial intelligence, you can do this with machine learning. We also do that a lot. But the interpretation, and of course, a machine can compare to spectrum and say, well, it appears that here we are having some carbon dioxide or some carbon monoxide or some methane. But what this actually means, it's for the scientist to decide yet. So the artificial intelligence cannot decide, well, this means this or that. So I think does it answer your question? We as a scientists are the ones that are interpreting the data, even though a lot of the analysis can be done through artificial intelligence or even machine learning. But it's up to us to decide on these things. So moving on to the next part, here, if you click here, you go to the change composition section, in which you have all the molecules that we are including in the planetary atmosphere of Mars. So what we have here is carbon dioxide, nitrogen, some oxygen, some carbon monoxide, some water, some ozone, and also some scattering aerosols. Mars has a lot of dust. Sometimes it has dust storms. So if you want to check the impact of dust in the planet, you can adjust here the amount and the abundance, or the abundance of any molecule in the atmosphere that you're interested in. And it also provides a vertical profile, the thing I told you about, on Mars. So here you can see how the temperature in the atmosphere of Mars varies as we go further up in the atmosphere. What you can see here is that it has a small stratosphere, which is where the tropospheric tendency of the temperature going down with height is inverted due to some photochemistry happening on Mars. And then you have the mesosphere, and then you have the thermosphere again. As the temperature rises up, because there are very few particles, it doesn't even make sense to talk about temperature anymore here. And then you also have the abundance of the different gases. So here you have CO2, here you have nitrogen, here you have oxygen, and carbon monoxide and water, as a function of altitude in Mars. So you can vary all these parameters and then see how, by varying one or the other, how that affects the whole spectrum of Mars. And then you also can vary the surface. that you are interested in observing. Planetary spectrum generator has a very interesting model just for small planetary bodies, so something like asteroids, comets, which have different sort of characteristics than a planet has. And you can also use it to model what kind of surface emissivity or even composition that planet or airless world has. And you can even have like profiles here for water ice clouds, dusts in the atmosphere. As you can see, it stays a little bit closer to the ground because dust doesn't go further up in the atmosphere, and some ozone as well. And then you can change the instrument. So here we are trying to observe Mars with JWST. So we're simulating as if we were going to observe Mars with James Webb Space Telescope. And what do we have? Well, we have all the characteristics of the planetary spectrum of the instrument, of the telescope that we're using. It has an effective diameter of 6.5 meters. You have some of these exposure times set. You can play with all these factors. And you also have the resolution, which is low for the James Webb Space Telescope. If it was with the VLT instrument, it would be high resolution, but then you'd have the Earth's atmosphere in front. So for instance, here, we're not applying the terrestrial transmittance, which is the fact that we have an atmosphere on top of us. For James Webb, there's no atmosphere, it's in space. So it's not going to have Earth absorption lines spoiling your spectrum. And these are the wavelengths that we're trying to probe. So James Webb probes the near infrared with some of its filters. It also observes in the mid infrared with some other filters. But this is for the close infrared. And we can save settings and generate the spectrum. So let's see what we get from here. We generate the spectrum. You can all do it. You can all go do this at home by yourselves after this talk, because it's very useful and it's very user friendly to use. What we get from that, we have the simulated spectrum of Mars as observed with James Webb. Just by looking at here, if you're not very practiced at this, you might not see much. We see that there's some very strong absorption here at 2.7 microns. We have also this strong absorption here at 4.3 microns. We also have something here, and also something there, but we don't really understand what this is. And I did not understand what these different absorptions meant. And that's why it's so cool that Planetary Spectrum Generator has this this plot below that tells us what is in fact absorbing here. So you can see that as I click on and off for the CO2 transmittance, it shows us that what is absorbing here is CO2. This is basically how transparent each gas is for the light at a given wavelength. So if your gas is very prevalent in the atmosphere and is very opaque in the atmosphere, then it is going to produce these very strong absorptions, which, as you can see here, that are caused by CO2. Let's remove CO2. What other things do we have absorbing here in our atmosphere? Oh, we have some water. You can see that there's water here. And if you look up there or here, you might be able to find a strong, weaker, but also prevalent absorption. And we also have, what is this? Carbon monoxide. So this absorption band here, it's probably caused by carbon monoxide. And then you also have some of the noise components and the stellar transmittances that the model considers that are very useful for the analysis. Just as a... So you can all go home, play with this, and it's really intuitive, and it's a really useful tool to actually understand what planetary astrophysicists do when they try to, when we try to observe a planetary atmosphere and the planetary spectrum, and really play and try to understand, oh, if there's an absorption here, it means that there's CO2 in the atmosphere. And if there's an absorption there, it means that it is water. And so we do this kind of work to allow us to understand what other planetary atmospheres are made out of. And just as an example, we can try to simulate the an exoplanet transit of a specific exoplanet with James Webb. Let's try Kepler 10b, which is thought to be a lava planet. So as you can see, its surface temperature is almost 500 degrees. It's a very dark planet, and we're going to observe it in a wide wavelength range with a low resolution. We click here, and what are we going to see? We see the planet going in front of the star, and we see the contrast between the planet and the star. So the higher the value here, unlike before, it means that something is absorbing. And what we have here absorbing, it's CO2 again, but we also have this other thing, which is water. So the planet also has water, and the planet also has, well, some other gas that you might put in there. So what this means is that you can play with the abundances of the gas you want to play with, and from there you can simulate what the spectrum will look like. And if you have access to observations, then you can compare these models with observations and detect actually molecules, clouds, and whatever you want to detect from a planet. So that was basically what I wanted to share with you today. I hope you find this relevant and useful, and if you have some questions, I'm very open to answering them. So please, that was what I intended to show you. So
thank you, Rafael. It was so very, very interesting. It was incredible to see how you actually do this analysis of this data. So there is one question. One person is asking, like, where can we find the resources to learn more about these special courses or something? Do you know any platform where we can find this information and learn from? Y en español, pues le pregunto que ponía en el grupo por algún lugar donde, si él conoce alguna plataforma, algún sitio donde podamos encontrar algún curso donde podamos encontrar más información o cursos para aprender de estas herramientas.
Well, I'll send here in the group the web page of the Planetary Spectrum Generator, which is this one. You can go there by yourselves. And this page actually has lots of documentation attached to it. So you can go there to this web page. This is the website I've been using. I don't know if you can access it, but so yeah, you can go there, and it also has some videos, I think, and some YouTube videos. If you just Google Planetary Spectrum Generator, you can go online and see videos about this and more detailed analysis than what I just showed here, which was very introductory. And the site itself, the website itself, is very user-friendly. So you can just go there and see for yourself how to use it, and like it explains everything that it does, how to like that. There's like even a user manual which you can go to this website and try to use. So I think it's very useful. That's why I wanted to share it with you, and everyone can use it. It's free, open access.
Excellent. I have a question for you. So you were saying that for doing this analysis, you basically need basic information, so like a pattern of that planet, something that you already have, and then the data that you are recording, and then you compare both of them, and then you have new results. What happens if you are trying to analyze the atmosphere of a celestial body that you don't have any recording before, so you don't have this pattern? What's the strategy that you use?
That's a great question. So we always try to have an educated guess of what the thing that we are trying to observe looks like. So if you're trying to apply for time in James Webb Space Telescope, in Hubble Space Telescope, in the very large telescopes there in Chile, or in the big telescopes in the large island of Hawaii, in Mauna Kea, actually I and my team, we've used a large telescope in Hawaii, the IRTF, which is from NASA. This last February, we used that telescope remotely, so we were controlling it from Lisbon. It was really fun. But to get time in those telescopes, you need to write a very detailed proposal, which basically says, well, I want to observe this body, this celestial body, either this planet, this star, this exoplanet, because I want to see if it has this or if it looks like that. or if its flux is like this or that. And then you present your science before you get the results. And then if they think that your science is good and that your you explain it well and the telescope is actually useful to do that kind of science, and then you have to convince them of that, they give you some time, and then you do the observations, you get the data, and it's nothing like you expected before. Well, you always have to start from some place. If you're going to observe Venus or a Venus-like exoplanet, well, you expect it to have perhaps clouds and to have some CO2 in the atmosphere, to be very hot. You can use these different previous pieces of knowledge to advance your knowledge further and to try to obtain new information about these planets and exoplanets. Now, that's a very valid question, the one that you asked, because I just came back from a conference in Vienna in which we were discussing some of the key scientists in this area were presenting results from James Webb of some new observations of the TRAPPIST-1c planets and TRAPPIST-1 system, which is a system of 7 planets around a very cold star, an M dwarf. And it's very fascinating because they all transit the star, so we can observe, and it's one of the closest exoplanet systems to us, so we can really observe all these different rocky planets that appear to be around the star. And they're trying to observe the second planet there. So the first one, they know it already, it doesn't have an atmosphere, so it's something like Mercury. But then the second planet, they thought it was going to be like Venus, but its spectrum still doesn't look like anything we know yet. So it doesn't look like Venus spectrum, but we still have very few measurements. So out of the very few measurements that they have, they spent like a whole afternoon in the conference trying to discuss, well, maybe it looks like this, or maybe it looks like that. It was fascinating to witness. But the thing is, there's a lot of stuff we don't know, but we have to start somewhere. So we make our educated guesses, and then using statistics, we see if our model fits the data or not. And as you get more data, you'll get better models as well. And so they go hand in hand until you have a more detailed and definite answer. And once you have a better defined answer for these planets, you'll go to some other planets and try to get from these previous pieces of knowledge, what can we learn afterwards? I hope I didn't. I hope I answered your question.
Absolutely, it was great. So I'm curious about what you last said. What's the atmosphere like then for this planet that you were talking about? What is like? What is life? Like, I don't know, like a rocky planet or?
Yeah. So the TRAPPIST-1c1. So the TRAPPIST-1 system is composed of 7 planets, and we can know their radius because of the area of the star that they cover. So we can know their radius, and we know their mass because we can also see the star, the effect of the gravity of these planets on the star. So if we know their radius and mass, we can know their density. And that means we can know that most of these planets all of these planets are small and probably rocky. So except the outer ones that are a little bit less dense, so they could be something like icy moons, but large. It's very weird, and as you go look beyond our solar system, we see very different kinds of planets that we do not have in our solar system. So it's a great testing ground for these worlds. So in these planets, we would expect some of them to look a little bit like Venus. And one of these planets, which is TRAPPIST-1d or 1e, so either the third or the fourth planets in that system, is actually inside the Goldilocks zone. So which is the place around the star, which should have about as much irradiation as the Earth has. So we could have liquid water in the surface. But we don't really know yet because we don't yet have spectra of those exoplanets because it takes a lot of time to get enough observations to build up statistics before we can make some decisions. But in the next few years, we'll surely have data from TRAPPIST-1c, 1e, 1d, 1f. And we'll get to study all these planets' atmospheres. And we'll be able to understand if they are more like Venus or more like the Earth, for instance. And what's the difference between Venus and the Earth? It's a dramatic difference. Like Venus has a 92 atmospheric pressure, equivalent of atmospheric pressure to the Earth's at its surface. So it's like having 92 Earth's atmospheres on top of each other at the surface. And the surface temperature, due to a runaway greenhouse effect, that is enough to melt lead on the surface. So it's completely hellish in comparison to Earth. It has lost all its water, but it sits on a part of the orbit around the sun that is actually a little bit, it's in the inner edge, but it's still inside the Goldilocks zone for Earth, for our solar system. So if you look at an exoplanet outside of our solar system and it's in the Goldilocks zone, it could very well be not an exo-Earth, but an exo-Venus. And being able to distinguish between these two will be fundamental to decide if, and to understand if we are finding a habitable planet out there or something as hellish as Venus. And that will also allow us to understand what happened in our own solar system and that caused Earth and Venus, which have about the same mass and the same radius, and are in the very same zone of the planet of the solar system, to be such dramatically different planets. So that's also the reason why we're so interested in looking at Venus-like or Earth-like exoplanets out there, to be able to understand what happened here on Earth and what happened there on Venus. This is something our group is very interested about, and I'm pretty sure we'll get very interesting results about that in the near future.
That's amazing. So I have a couple of questions here for you. Rosemary dice, ¿hay suscripciones pagadas para acceder a los datos de estos observatorios de los que mencionabas?
I would say no, but I will actually say more or less. So these observatories, like, for instance, ESO, the European Southern Observatory, which has all those observatories in Chile, it takes a lot of money to build those observatories. So the countries that pay for the construction, which are basically a consortium of European countries and Chile, because Chile, is the host country, are paying for it. For instance, Portugal is paying as well. So I think we have access to some time in some of the instruments, but there's the majority of the time in these telescopes are actually free to use. You don't have to pay for it. You just have to submit a proposal, and your proposal has to be very good. I personally have submitted proposals to these observatories in ESO 3 times already, and I haven't yet won any. So I still haven't had the time, because they're very competitive. It's really, even if your science is very good, it's very difficult to get time in those observatories, because everyone wants to get them because they're the best in the world. The same thing goes for the Hawaii telescopes. And in that case, we have already won some observations there. My team has also won some observations in Chile as well. I personally haven't, but I've applied to some for this next month. So I might get the results in June. So if I get them, I'll let you know if I got the results and if I got the time there. And if I get time there, well, then we can use that to make our science project and to observe our targets. But it's very challenging. I wish it was just paying, but it's not just paying. It's having the best science and the best science proposal to submit there. So it's very competitive, and everyone in the world wants to get it. Yeah, so that's it.
Of course. Entonces, Juan Carlos Bazán pregunta, dado la distancia que hay en los exoplanetas, al tener el espectro, ¿no se produce ruido con su estrella u otros cuerpos celestes cercanos?
Absolutely. That's a great question. I wouldn't say with corpus celestes cercanos, but with its star, of course, it's a very important source of noise. When you're looking at an exoplanet around a star, it's like looking at a moth, a small butterfly, in front of a lighthouse or like a faro. I think that's how you say it in Spanish.
Yes,
so it's having a very small thing, thousands of times dimmer than a very bright object right beside it. So when you try, that's why we need so many observations. That's why we need statistics. And the more observations you have, the less noise the more you'll be able to reduce the noise of your observations. And if you reduce the noise, that means you can detect fainter and fainter things in your atmosphere of your exoplanets. I'm actually now starting to work with exoplanet spectra. So far I've only worked with Venus and Titan. I'm starting to work with exoplanet spectra that we got from VLT Expresso, which is one of the best instruments here in Portugal. And boy, is it noisy. It's very noisy. It's very noisy. So you need, so for instance, just to give you an idea, instead of one exposure, like instead of taking one photograph to the exoplanet, we have to observe it for nights and nights and nights, for several nights, so that we have enough observations that allow us to remove the effect of the star and get only the effect of the planet in the spectrum. And even so, it will still be noisy. The problem is not that it's noisy, it's how noisy it is. And the more observations you have, well, the less noisy it will be. So that's it.
Excellent. Pablo Manuel Hedera pregunta, those simulations you just shown present useful data for each analyzed celestial body. Is there a way to save them for future data analysis?
Of course, I forgot to mention that. That's a great question. Thank you so much. In the planetary spectrum generator section, I can share it with you again if you don't mind. Yes.
Sure, do it.
You can see it here. So imagine that you wanted to get this spectrum here. You are very interested in studying this exoplanet. You got the simulations very well. So the thing you can do is literally clicking here, download, and you'll get the TXT file being downloaded to your laptop, to your computer, and that will allow you to. Can you see what I'm sharing the screen here? It's
yes.
Literally clicking here in the button download. So you'll get a TXT file that has the wavelengths and the absorption and the flux of your planet or the contrast. And you can use this for further data analysis, of course. We take these TXT files that are downloaded, and then using very simple Python code, we can compare it to the actual data that we got from the observatory. We put them side by side, and we see if it fits or not. And what we usually do is actually, swiping, making several simulations with different characteristics. So varying the abundance of a given species in the atmosphere and seeing which of them fits the better to your results. And then that's probably the one that's better and closer to the truth. So that's it. I hope I answered your question. Hi. Oops.
Tu micrófono, Karen.
Yes.
Thank you.
That's it. Yeah.
So I was asking just one more questions. Regarding to the data you show us before, how can you use that, or which is the process to use that, or if it's still possible to generate some kind of modeling of future scenarios or past scenarios?
Not sure I understood the question. So
basically that we see with the data you show us is like how we see it now with the time that we recover that information from the point where it starts to the Earth, right? But what happens if I want to explore why the atmosphere of one celestial body now is absent or something? Can I recover that information doing some kind of modeling with the data we have now?
You can do that, but for that you need different kinds of models. So the models I've shown you, they simulate the atmospheric. So they simulate the atmosphere with the conditions you give it to simulate. It's literally like a function, like a machine. You give it the input, it will give you the output, which is the spectrum. To understand how the atmosphere actually evolves over time, you need to do other kinds of models. Which are completely different. Like and I want to learn more about those models. I myself don't know a lot about them yet, but I really want to work on that. It includes geochemistry, atmospheric sciences, oceanography even. You need to combine all this expertise to model how the atmospheres of planets will evolve in millions of years, and why the Earth's atmosphere is like it is, and why Venus' atmosphere is like it is, or any exoplanet atmosphere is like it is.
Okay. I'm asking that because I think it's very important for the planets that we were guessing that something will happen to lose their water or something like that, like what happened with Mars. And if we know that it's possible to get to that kind of modeling with this data, is kind of cracking the way to do that.
Yes, people are doing it. Actually, very funny thing that you can see in some exoplanet spectra is actually the planet losing water. We see that today on Venus. If you get a spectrum of Venus, and if you do a retrieval of where the water is emitting in Venus atmosphere, so you can get an idea of where the water is on Venus atmosphere, you see that Venus today still has too much water in its upper layers rather than being in the downward layer. So that basically means that Venus is still losing water today, even though it is dry as a bone. So that tells us that the planet is losing water, that it had probably had a lot more water in the past, and we still don't know why it is losing water, but it's probably because it's very hot and it's quite hellish. And you can actually see that for some exoplanets as well, to see that the place where the water is absorbing or emitting, because if the water molecules are in different conditions, either at the top or the bottom of the atmosphere, they will interact with light in a different way. And you can check that, and you can see if the water is on the top or the bottom of the atmosphere. And of course, just like here on Earth, if you have water in, like on Earth, for instance, you don't have water above the troposphere. So if it's very rare to have water in the stratosphere of Earth. It's a very dry area of the Earth's atmosphere. And that's one of the reasons why all the climate on Earth is on the troposphere, and why you don't have any climate phenomena on the stratosphere. And once things break that barrier between the troposphere and the stratosphere, like for instance what happened with the Hungatunga volcano 2 years ago, where a column of ash was thrown into the stratosphere, more than 50 kilometers in height. It put a lot of water and a lot of moist and ash into that layer of the atmosphere, and it completely changed the way it works. It's very fascinating to observe these things happening, even here on Earth. So yeah, that's it.
Excelente. Muchas gracias, Rafael, por la increíble explicación, toda la explicación de cómo funciona la plataforma, cómo manejar estos datos. Solamente recordarle a la gente que esto ha sido grabado, entonces también pueden encontrarlo nuevamente en el YouTube de la Red Boliviana de Ciencias Planetarias y Exploración Espacial, para poder repasar nuevamente cuál es el proceso para analizar estos datos, generar nuevamente, analizarlos. Y nuevamente quiero agradecerte a ti, Rafael, por darte el tiempo de explicarnos todo esto. Sé que sí es a veces un poco complicado cuando no es en un idioma que manejamos tan técnicamente, pero te agradezco muchísimo toda la predisposición a nombre de toda la red. Y antes de finalizar, sí quisiera hacerte una consulta más casual, que es, hay mucha gente acá en Bolivia que está muy interesada en todo el estudio de todo lo que está relacionado con el espacio y las ciencias espaciales. Y quisiera que le des un consejo a la gente para que pueda seguir este camino, ¿no? Tú sabrás, en Bolivia no hay muchas instituciones, no hay mucho impulso hacia esto, entonces, ¿cómo puede la gente boliviana poder llegar a estos objetivos?
Well, my answer, or mi respuesta es, well, it's worth what it's worth, pero les puedo dar el ejemplo de lo que pasó aquí en Portugal. Hacia 40, 30 años no teníamos un instituto que hacía astrofísica aquí en Portugal. No teníamos nada de esto. Pero lo que ha pasado es que algunas personas que querían hacer esto, han ido a otros países, o Alemania, o Francia, Inglaterra, Reino Unido, a Estados Unidos de América, bueno, otros países en Europa que estaban más desarrollados en estas áreas que Portugal. Y algunos de ellos volvieron y con su expertise que adquirieron en esos otros lugares, empezaron sus institutos de investigación. También hubo voluntad política de haber dinero para que les apoyaran en esos proyectos, pero la gente quería volver aquí a Portugal y empezar a esos institutos de investigación que tenemos aquí hoy. Una de esas personas, por ejemplo, se ha graduado aquí en mi universidad y fue para hacer su doctorado en Ginebra, en Suiza, con dos investigadores que estaban en los años 90. Y fueron ahí y él se llama Nuno Santos. Y su equipo, durante su doctorado, ha descubierto el primer exoplaneta. Y sus dos supervisors de doctorado han ganado en 2019 el premio Nobel de la física. Y entonces él hoy está aquí en Portugal, en Porto, pero es el mismo instituto donde yo trabajo. Ya ha empezado a tener un equipo con muchos estudiantes y de posgrados y todo más en la universidad, en el Instituto de Astrofísica, y se ha empezado a desarrollar. Lo que yo quiero decir con esto es que no es imposible empezar desde cero, porque eso es lo que ha pasado aquí hace 30 o 40 años. No es fácil, es importante que el gobierno, que las instituciones de las universidades tengan recursos para que apoyen a estos investigadores que han ido al extranjero y han venido. También les ha apoyado a irse para que pudieran volver y hacer de nuevo más desarrollo en esta área. Por eso, sí, muchas veces lo importante es que basta una persona irse al extranjero y volver con ideas nuevas y capacidad, pues, de empezar todo un trabajo de nuevo. Lo mismo ha pasado con mi supervisor aquí en Lisboa, que estuve en París y volvió y empezó un grupo de investigación aquí. También con mi otra supervisora en otra institución que estuve aquí en Portugal, que ella es una química y astroquímica. Estuve en Leiden, en Imperial College de London, y ya ha volvido aquí a Portugal también para empezar su grupo de investigación en astrobiología aquí. Entonces, cuando no hay en esos países, pues no es fácil y puede ser muy caro, pero si algunas personas pueden irse y volver, después puede ser que empiecen a crear condiciones para que las personas de la generación siguiente, como es mi caso, puedan ya desarrollar sus proyectos en su propio país. Así lo es. Y espero que pues, eso pueda pasarse en Bolivia también.
Seguro que sí. Muchas gracias por compartirnos la experiencia de Portugal. Seguramente eso también va a abrir mucha idea a la gente que nos está acompañando ahora y a la que se va a unir a las siguientes charlas. Aprovecho para decirles eso, que cada mes hay una charla diferente, así que pueden estar atentos a las redes que tenemos para saber quién viene, con qué tema y se puedan unir también a estas charlas. Rafael, nuevamente quiero agradecerte por el tiempo, por la increíble explicación para todos nosotros. Esperamos tenerte en el futuro, en alguna nueva oportunidad y poder seguir escuchando las investigaciones y los resultados que estás obteniendo, que suenan increíbles.
Me gustaría muchísimo irme a Bolivia también. Puede ser que una de las próximas presentaciones sea en Bolivia, no sé.
Esperemos que sí, que pase. Bueno, gente, muchas gracias por estar acá, por acompañarnos. Mi nombre es Karen Los Santos y a nombre de la Red Boliviana de Ciencias Planetarias y Exploración Espacial, quiero agradecerles a todos ustedes y nuevamente fomentarlos a seguir viendo nuestras redes para que puedan acceder a las siguientes charlas que vamos a tener y también recordarles que en el YouTube que tenemos van a poder encontrar esta charla. Gracias a todos y nos vemos en una siguiente oportunidad.
Gracias.